Compare these two identities. On the left is the standard binomial expansion. On the right is a relation defining the Bernoulli polynomials. The structural symmetry is near perfect. In the 19th century, mathematicians used this similarity to justify a strange shorthand. By dropping exponents down into the subscript position, they found they could manipulate polynomial indices as if they were simple powers. This operation is logically incoherent. An exponent is a mathematical operation, repeated multiplication. A subscript is merely a label, a way to keep track of a sequence. Yet this umbral or shadow calculus consistently produced correct results. By pretending labels were operators, mathematicians derived complex identities proven true through difficult traditional means. Mathematics cannot rely on coincidental notation. The reliability of these umbral proofs suggested that the notation was actually a window into a rigorous, formal symmetry between sequences and algebra that had not yet been defined. Gian-Carlo Rota addressed this in the 1970s. He wanted to move past the magic of umbral manipulation and find the actual algebraic mechanism that made the trick work. He realized the shadow was actually a linear functional, a map that takes a polynomial and returns a single value. By defining a functional L that maps z to the power of n directly to the nth Bernoulli number, the mystery of the shifting index disappears. When the functional replaces the subscript, the exponent returns to its proper role. Because the functional is linear, we can pull it out of the summation, proving the umbral trick is just a consequence of standard algebraic properties. Rota's framework provided a way to translate the behavior of continuous polynomial sequences into the language of discrete algebra. This wasn't just about cleaning up old notation. It provided a blueprint for abstracting more complex operations, like the integral, into symbolic rules. We can apply this same rigorous abstraction to the cornerstone of continuous analysis, the integral. This is the integration by parts formula, relying on curves, limits, and infinitesimal change. To abstract it, we define operator p to represent the act of integration. Rearranging isolates the operator products, leaving a purely symbolic relationship between two p operators. This is the defining relation of a Rota-Baxter algebra. Variables and limits have vanished, leaving behind a standalone algebraic rule for how two integrals interact. By treating integration as the operator p, the mechanics of calculus are isolated from the geometry of curves. Integration is now a symbolic property that can be studied as a discrete system. We can broaden this by introducing a family of operators, each representing different bounds of integration. This results in the omega Rota-Baxter equation, which adds a weight term, lambda, to account for how these operators overlap. The challenge is to build a free algebra, a system that obeys these rules without relying on actual calculus. Mathematicians solve this using planar rooted trees. Their inner edges represent operators, labeled with omega indices. Angles between branches are decorated with variables like x and y. Finally, grafting a tree to a new root node represents applying an integration operator. Every part of this tree, the edges, angles, and grafts, is engineered to act as a physical placeholder for an operational property of calculus. To make this a functional algebra, we need a rule for multiplying two trees together. This is the recursive diamond product. The product works through recursion. When two grafted trees multiply, the rule forces them to split and recombine into a sum of three new tree structures. One where the first operator contains the second, one where the second contains the first, and a third where the branches fuse. These three tree structures correspond exactly to the terms in the omega Rota-Baxter equation. The nested branches mirror the nested operators, and the fused branches represent the lambda weight term. The tree geometry calculates the integration by parts formula automatically. Because the geometric recombination of the branches perfectly mimics the algebraic relation, the multiplication of trees becomes a perfect simulation of abstract calculus. Since the set of all possible trees is closed under this product, these structures successfully generate a free omega Rota-Baxter algebra. This completes the translation of continuous integrals into discrete, symbol-based combinatorics. The 19th century mathematicians who manipulated indices like exponents were on the right track, even if they couldn't explain why. They were seeing the first hints of an algebraic framework, where the rules of calculus exist independently of the curves they describe. Whether using Rota's linear functionals or these planar rooted trees, The logic of the integral maps onto the logic of symbols. This allows us to treat the rules of calculus as combinatorial properties, turning the study of change into the study